Hello and welcome to the third video of the M2 chapter Variable Acceleration. Quick integration question on the screen to get us going for the pure stuff we're going to be using in this video. Find f of x, given that the derivative of f of x is this, and the information that f of 2 is equal to 1. I hope you remember that this is a boundary condition to help us find the constant of integration. So f of x is equal to the integral of the derivative of f of x with respect to x. So it's the integral of 6x squared plus 2x minus 7 with respect to x. And of course we do each of these terms separately. 2x cubed plus x squared minus 7x plus the constant of integration. Now we use the boundary conditions information. When x equals 2, f of x equals 1. To find the value of c, which in this case is minus 5. So the final function, rewrite it with the value of c as minus 5. In this video, we're going to use integration to solve kinematic problems, just like we used differentiation in the previous video. Just as we can differentiate functions of time, we can also integrate them. Given what we had in the previous video, this and this, I hope it's fairly obvious that we can just work backwards. The reverse process integration gives us these two statements, that the displacement is equal to the integration of the velocity. So if you have a function for the displacement, you can differentiate it to get the velocity. But if you want to go from the velocity to get a function of the displacement, you have to integrate that. Same over here, you can differentiate velocity to get acceleration. You integrate the acceleration to get back to the velocity. As you're doing these questions, don't forget, as we had in the starter there, the constant of integration. That's very important. It needs to be in your function. If you don't know what it is, leave it as a constant c. But if you've been given boundary conditions, you should work out what that is and put it in. Something else that's worth noting here is that these tell us the area under a velocity time graph. When you integrate the velocity time graph, you get the displacement. Now that might be something you've heard before. The area under a velocity time graph is equal to the total distance traveled, or the displacement. It also tells us here that when you integrate an acceleration time graph, you get the velocity, more specifically the change in velocity of the object as it moves. This again is just linking the idea of integration with area, something you've seen before, but in this case it has a real-world interpretation. Okay, that's all we're going to do for the notes on this because it's very similar to the differentiation, and you've done integration and differentiation before in pure. So let's jump into a few examples. A particle p is moving on the x-axis. At time t equals 0, the particle is at the point where x equals 5. I hope you recognize already that that is a boundary condition. The velocity of the particle at time t seconds, where t is greater than or equal to 0, is this, meters per second. So here's our function, v equals this. Find an expression for the displacement of the particle from O at time t seconds. So we've got an expression for v given in the question. V is 6t minus t squared, and we want an expression for the displacement, which we now know is the integral of the velocity with respect to time. That gives us the integral of 6t minus t squared, which is 3t squared minus t cubed over 3 plus our constant of integration. Then we go back to our boundary conditions. At time t equals 0, x is equal to 5. Okay, I've been using s instead of x. Let's change that to match the question. So x is 5 when t is 0. Well, when t is 0, this is 0 and this is 0. So it's just c equals 5. So my final expression for the displacement is 3t squared minus t cubed over 3 plus 5. That's part A. Part B, as usual, is now going to get us to use this function. Find the distance of the particle from its starting point when t equals 6. Now just be a little bit careful on this question, because the starting point is when t equals 0. And usually we would expect that to be x equals 0, but in this case it's x equals 5. So my starting point is x equals 5. I need to take that into account when I finished calculating when t equals 6. So when t is equal to 6, x is equal to 3, 6 squared minus 6 cubed over 3 plus 5, which is 41. So now we know that when t equals 6, x equals 41. And we need to compare that to its starting point when t equals 0. At t equals 0, the particle is at x equals 5. So we actually need to do one more step, 41, the point where it is at t equals 6, minus 5, the point where it is at t equals 0, to give us the distance from its starting point as 36 meters. Next example. A particle is moving in a straight line with acceleration at time t seconds given by this, where t is greater than or equal to 0. The velocity of the particle when t is 0 is this. Again, here's a boundary condition. Find these things here. A quick note here that it's moving in a straight line. That's just nice and formal. It's trying to clarify that there's no circular motion. It's not going around corners or anything. But it could still go forwards or backwards on that straight line. I don't think it will in this question, but just a quick note there. Every time you see this, it's just cutting out the option of circular motion. It's not saying anything about forwards and backwards. So we need to find an expression for the velocity at time t seconds. We know that the velocity is equal to the integral of the acceleration with respect to time. And we know that the acceleration is cosine of 2 pi t. Integrating this gives us sine 2 pi t divided by the derivative of the function inside the brackets, 2 pi. So you get 1 over 2 pi sine 2 pi t plus the constant of integration. Now we need the boundary conditions. When t is 0, this whole sine function becomes 0, so this whole first term becomes 0. V is 1 over 2 pi, so we end up with 1 over 2 pi is equal to 0 plus c, so that's our value for the constant, giving us the final equation of v is equal to 1 over 2 pi sine 2 pi t plus 1 over 2 pi. That's an expression for the velocity. Now we need to find the maximum speed. To find the maximum speed here, I might do something you're not expecting. Usually I would differentiate, set it equal to 0. We don't need to differentiate, we've already got it here. So you could set this equal to 0, find the time, put it in here. But because this is a sine function, and I'm just trying to maximize this, I know that the maximum of this is going to happen when the sine has its maximum value of 1. So when sine is equal to 1, we get 1 over 2 pi plus 1 over 2 pi. And that is equal to 1 over pi meters per second. And you'll get the same answer if you go through the process of setting this is equal to 0. The inverse cosine of 0 is pi by 2. Divide that through, and you'll get t is equal to 1 over 4. Over here, t is equal to 1 over 4 gives you sine of pi by 2, gives you a 1, which gives you the same value, 1 over pi. Part C, the distance travelled in the first 3 seconds. Now here I need to be just a little bit careful. It's not saying what is the distance at time t equals 3, it's asking for the distance travelled from t equals 0 all the way up to t equals 3. And I need to be a little bit careful, because if I connect that again with the area under a graph, you know that if it looks kind of like this will come up as positive, and this will come up as negative. And they will cancel each other out if I just do the calculation from here to here. For distance, what I would need to do is calculate separately this part and this part, turn this part into a positive value, and then add them together. So I would strongly recommend drawing a diagram here, just to make sure that you've got no parts underneath the x-axis. What we're going to be doing to find the distance travelled is integrating the velocity function. So this one here is the one that I want to sketch and check that none of this is beneath the x-axis. I can do that reasonably easily because of what I've drawn here. I know that the sine curve looks kind of like this. So what would normally be the minimum point would be here at 3 pi by 2. If I put 3 pi by 2 in here, I get minus 1. But if I do that, I get minus 1 over 2 pi plus 1 over 2 pi, which just gives me a 0. So the minimum value of my v is 0. So actually this looks more like this. And I don't need to worry about a negative part of this calculation. That would be the first second, and then you know that a sine curve repeats. So it would be from there to there, all of these bits here. And as I just said, none of that is beneath the x-axis, so we don't need to worry about negatives. For more involved questions, that is something to consider though. So here we're okay. We can integrate from 0 up to 3 seconds. So from 0 to 3, we're integrating the velocity function to give the total distance traveled. Doing that gives us 1 over 4 pi squared. Sine integrates to give negative cosine 2 pi t plus t over 2 pi. And we don't need a constant of integration because we're putting in the limits 0 and 3. When you put 3 in here, you get 6 pi. Cosine of 6 pi is a 1. When you put 0 in here, cosine of 0 is also a 1. So each of those are going to give us a 1, which means that we get minus 1 over 4 pi squared plus 3 over 2 pi minus 1 over 4 pi squared plus 0. The first term of each bracket cancels out to give us the final answer of 3 over 2 pi. And that is a distance, so we've got meters. Our final example, a particle travels in a straight line again. After t seconds, its velocity v is given by this function, where t is greater than 0. Find the distance travelled by the particle in the third second of its motion. Now again, this is different to what we've had. This is not when t equals 3, find the distance where it is. Neither is it find the distance travelled up to the third second, but it's in the third second of its motion. So in the first second, that's 0 to 1. The second second is 1 to 2. The third second, that is from t equals 2 to t equals 3. So we need to integrate between these two values. But again, we want to make sure that we're not crossing over the x-axis on the graph here, where part of this might be positive, part of it might be negative, and if we did that, we wouldn't even know we were getting the wrong answer. So first I'm going to sketch a diagram to make sure we know that this is all on one side of the x-axis. The diagram I'm going to draw is v versus t. So we've got v here, t here. We can see it's a quadratic. When t is 0, v is 5, and the t coefficient is 0, so this is going to be symmetrical about the v-axis. Not the best diagram, but good enough for our purposes. So what I want to make sure is that this crossing over of the t-axis does not happen between t is equal to 2 and t is equal to 3, because then I'm going to have some parts of the area cancelling out in the calculation, and I would have to split it into pieces, like I said in the previous one. So the key point to know is, when does this cross the t-axis? That's when v is equal to 0. So I'll quickly do that on the side. 0 equals 5 minus 3t squared gives us 5 over 3 square root of, plus and minus obviously, but the negative one we're not interested in. Root of 5 over 3 in decimal form is 1.29. So we're okay. 2 is on this side, and 3 also obviously is on this side. So when we integrate between these two, we're going to get this area here, and that does not have any parts crossing over the x-axis or the t-axis, so it will give 1 full solid answer, which is great. The only thing to note here is that it will give a negative answer because it's underneath the t-axis. So if we want a distance which can never be negative, we'll just have to turn that into a positive at the very end. Our calculation, though, does not need to be split up. We just need to integrate from 2 to 3. And we're integrating the v function, which is this. We get 5t minus t cubed. And again, no constant because we have limits 2 to 3. And that gives us 5 times 3 minus 3 cubed minus 5 times 2 minus 2 cubed, which is minus 12 minus 2 minus 14. So the displacement is minus 14 meters, but because we're working with distance here, we need to turn that into a positive value. So the distance traveled is 14 meters. So there were a few things in there to be careful of. First of all, understanding exactly what it was the question was asking in terms of time frame. Then to be clear that you could integrate from this time to this time without concern that you needed to split it into two pieces because of the sketch of the graph over here. If you wanted from time 1 to time 2, you would have had to have integrated, instead of doing this, you would have had to have integrated from 1 to 1.29, and then again from 1.29 to 2, making sure that you were using the absolute value of whichever one was underneath the graph, which would be this one, so you would need the absolute value of this one. I've gone through that fairly quickly on the side, but I hope that's familiar to you from the work you've done in your pure modules. I also hope that's enough for you now to have a go at some of the questions in exercise 2C, and maybe I'll see you for vectors in video 4.